Invitation and joining today's workshop. I'm Katie Jovanovska, Marketing Program Manager at Kumo, and I will be your host today. In today's workshop, we will be joined by Ben Berger, Data Scientist at Kumo, and Rishi Puri, Senior Deep Learning Engineer at NVIDIA. They will discuss how predictive context and graph-based reasoning can significantly enhance RAG-powered LLMs with practical examples using Kumo's platform and PyG. Before we begin, I would like to invite everyone to use the Q&A section to ask any question throughout this session. At the end, we will dedicate around 20 to 30 minutes to answer the most relevant question, and for the one we don't have time to answer live, we will follow up through email. Now I would like to invite Rishi from NVIDIA to begin this workshop. Rishi, over to you.
Thank you. Hello all, I'm a senior deep learning engineer at NVIDIA and lead our engineering efforts for PyTorch Geometric and research efforts for combining graph and language modeling. Today, I will be discussing GNNs and LLMs in PyG. Modern LLMs are built on the transformer model and excel at predicting the next token in a sequence. They are based on the attention module introduced in the famous Attention is All You Need paper from 2017. Since then, we have seen a tremendous progress in LLM research simply by scaling up model size in step with dataset size. However, we are reaching the limits of these scaling laws and are seeing a plateau in accuracy across the industry when it comes to simple autoregressive pre-training. One issue with autoregressively pre-trained LLMs is that their underlying predictive task is to predict the next token given previous contextual tokens. The problem is that this method of computational thinking is inherently single-hop in nature, which is far more simplistic than natural human intelligence. This single-hop logic then forms a sort of associative memory where, given context, they produce the most probabilistically relevant output tokens based on the distribution learned across their training data. As we are seeing today, basic LLMs as a single-hop memory bank are not sufficient for answering out-of-distribution questions reliably. This is an essential problem to solve since there is no limit to edge cases for areas where transformers are being used, like NLP, robotics, medicine, and more. Imagine your goal is to learn the sequence 2, 4, 6, 8, 10, and so on. Our general human intelligence can easily find a solution that will handle the entire distribution of data. Just given a number, return that number plus 2. However, an associative memory model, such as basic autoregressive LLMs, will likely fail on out-of-distribution examples. Imagine for training, we have 500 gigabytes of space to store our model's parameters. We could just directly store the next token in the sequence for every available token. This is what LLMs do today with gradient descent-based learning. The parameters will basically just store 2 to 4, 4 to 6, and so on. When we are testing, this will pass within the trained distribution, but will generally fail when we are out of distribution. The correct output is not well defined for the model, and in the case of LLMs, this often causes them to hallucinate. The point of these examples was to showcase how simple LLMs are much closer to an associative memory than general human intelligence. Now, I will talk about how GNNs can help. In general, an n-layer GNN learns to predict over n hops of information in the graph, which makes them excellent candidates for enabling multi-hop reasoning in AI systems. This is essential since multi-hop reasoning is a key aspect of human intelligence. An example of my 2-hop neighborhood is me, my friends, and all of their friends. Our research finds that GNNs can improve LLM accuracy. We believe this to be possible since the GNN provides a semi-orthogonal source of information. LLMs tend to be much larger than GNNs. This is because a transformer layer is essentially a GNN on a fully connected graph between tokens. However, the transformer uses parameters to learn the importance of each connection, while GNNs do not need to parameterize how entities are connected, since the graph data provides this information. As a consequence, adding in GNNs comes at almost no effect on the total number of parameters. For example, one could greatly improve the accuracy of an 8 billion parameter LLM with a GNN as small as 10 million parameters. Here we have a diagram of a made-up NVIDIA org chart. The question is, who is the shared coworker between Bob Joe and Ronald Coleman? At first glance, the answer may not be perfectly obvious, even to a human. But thanks to the highlighting of the key nodes and edges, the answer becomes obvious: Arno Schwarzenegger. Using PyG, a GNN plus LLM gets the answer right, while the corresponding LLM fine-tuned the same way fails to answer correctly, even though both models were fine-tuned on the same general knowledge toy dataset. The pure LLM approach I described is generally similar to most graph RAG workflows today, such as the one popularized by Microsoft. At a high level, I like to describe the GNN's role as highlighting the relevant nodes and edges for the LLM, improving upon these basic pure LLM graph RAG pipelines. This diagram depicts a general graph-based RAG workflow using GNNs as a prefix to the LLM's inputs. We start with a natural language query. This needs to be encoded by our LLM's tokenizer and encoder. In general, we know LLMs suffer n-squared complexity, where n is the number of tokens. We also need to use the query to retrieve a relevant contextual subgraph from a larger knowledge graph database, and then encode it with a GNN. The retrieval step is a key part of any RAG pipeline. I will go into further detail after this diagram, including the computation complexity. The computation for the GNN can be considered inconsequential, given that the GNN can have 1,000 times less parameters than the LLM, and the GNN only has to perform inference on a subset of a few dozen nodes. In detail, we also pass a textified version of the retrieved subgraph to the LLM encoder. Note that most graph RAG solutions do not use GNNs and only provide a textified subgraph to the LLM. As you saw before in my toy example, LLMs and even humans can struggle to understand textified graph formats. This is why our work of adding in GNNs to the pipeline is so crucial, as it enables the LLM to understand graphs. We then want to combine the embeddings from the GNN and the LLM encoder. This step is also computationally inconsequential. Lastly, we pass this into the LLM's decoder module to get our final response. In our work, we generally fine-tune the GNN and the LLM together. However, if you are constrained by compute resources, you can use LoRa for the LLM, or you can even freeze the LLM. In the case of a frozen LLM, the GNN essentially learns to embed the context subgraph into the latent space of the frozen language model. In general, LoRa will be better than frozen, and fully fine-tuning the system is the best. PyG expects a graph where each node and possibly each edge has a corresponding feature vector. When working with a textual graph, we normally store this as triplets of short strings. An example is the triple cats eat dogs. To convert this into a form usable by PyG, we need a model that converts strings into feature vectors. PyG sentence transformer takes in a list of strings and outputs a tensor where each vector represents the corresponding input string. This is essential for converting a textual graph into a PyG object that we can do retrieval and machine learning with. We need to call the underlying model 3 times for each edge in our graph. This is because for each edge, we must call this model on both entities as well as the relation. Since the model must be called so often, we use a small language model like ModernBERT for efficiency. Small language models are sufficient for this task since they generally tend to understand short phrases. As an anecdote, when I was in school, we would use now ancient models like GloVe and LSTM and could inspect that their learned semantic similarity was relatively accurate for short phrases. We generally only need large language models for large or complex bodies of text. As future work, we intend to measure the trade-offs for small versus large language models. The PyG master branch also supports Vision Transformer for embedding images as node or edge features. This slide zooms into the retrieval part of the previous diagram. If we start at the left of this slide, you have a knowledge graph source of some kind which can have millions or billions of nodes. To sample a subgraph from it, we use k nearest neighbors between the query and the node embeddings, followed by n-hop neighbor sampling. After this, you're left with likely thousands of nodes. Next, to trim down to the dozens of most relevant nodes, we apply the prize collecting Steiner tree algorithm, or PCST. This method is essentially a semantic similarity based graph traversal technique. This step is performed on thousands of nodes and has linear scaling, so we can consider it to be computationally free, while it brings major improvements in RAG accuracy. Our retrieval framework is implemented in PyG in a customizable way to support extension to domain-specific retrieval methods. Up until now, we have been talking about GNNs feeding LLMs. In general, this is useful for settings where we have user prompts that are conditioned on data that we can view as a PyG graph. The type of tasks are token-level tasks, such as question answering. The data flow of these tasks is as follows. We take our PyG graph and pass it to a GNN, giving some output. This output is then combined with the prompt in some way and passed to the LLM to get an answer. The opposite kind of problem is where we use an LLM to feed a GNN. In this setting, we have a graph where every node or edge has tokens attributed to it. This setting is for handling graph learning tasks such as node classification or link prediction. The data flow of these tasks is as follows. We use a sentence or vision transformer to get feature vectors for each node or edge. Then we feed this graph to a GNN for graph learning. The state-of-the-art method for node classification on the OGB leaderboards is the GLEM algorithm. This is an instance of LLMs feeding GNNs. Due to memory limitations, training a full end-to-end system where an LLM provides textual embeddings for every node is essentially impossible at scale. This is because you would have to store LLM activations for every node in the graph. As such, GLEM lets the LLM and GNN take turns iteratively improving themselves based on the learnings of the other in an alternating process. The implementation of GLEM in PyG is about 7 times faster than the original paper's code, using the same hardware. This PR introduces the new text-attributed graph interface, allowing users to explore their own datasets. It also adds additional support for LLM fine-tuning using LoRa from the PEFT library. This work is already optimized and available with the NVIDIA PyG container or in the master branch of PyG on GitHub. For the rest of this talk, I will dive into the details of GNNs feeding LLMs. The latest release of PyG comes with new GNN plus LLM features as one of the main updates. There are 3 new major GNN plus LLM features in PyG 2.6. First is the G-retriever model, which allows a user to easily combine any PyG GNN with any Hugging Face LLM for graph-based RAG tasks. The next feature is the Web QSP dataset for RAG question answering with knowledge graph context. The final feature is an example for how to train a G-retriever model on the Web QSP dataset. By default, this example uses a Llama 3 8B LLM with a graph attention transformer GNN. There is also a tiny llama flag for using a 1 billion parameter model, but you can easily swap in any Hugging Face LLM. In general, GNN plus LLM workloads are very compute intensive, and therefore GPUs are essentially a necessity. Running on CPU basically never finishes. In this case study, Neo4j used Stark Prime, a medical knowledge graph dataset made by Yuri Leskovic's Stanford group. Neo4j was able to use G-retriever to double the hit at 1 metric. The previous state of the art is a pure LLM approach, so this shows adding GNNs to LLMs has immense value when used on a high quality knowledge graph. The baseline of comparison is a 16% accurate 7 billion parameter LLM-based agentic graph RAG, while the new GNN plus LLM solution provides 32% accuracy. The new solution consists of a Llama 3.1 8B model using LoRa with a 10 million parameter GAT. This solution shows how much accuracy can be improved by adding a GNN for such an inconsequential parametric cost. They have open sourced their work on GitHub. We also wrote a blog about it together. Most RAG datasets only have unstructured text context. As such, there is often an additional task where we must convert unstructured text into a knowledge graph. Our existing PyG framework uses the simple KG format of triples of entity, relation, entity. As mentioned before, LLMs are specialized for unstructured text, so they're the ideal model for this task. As my solution to this problem, I have created the text-to-KG class in PyG. See the PR link for details. For knowledge graph-based RAG, the knowledge graph is your source of information, and as such, the quality of it is essential. Because of this, we chose the latest open source model from NVIDIA, served through NVIDIA Inference Microservices, or NIMs. I chose to use NIMs since most PyG users can't run a 70 billion parameter LLM. This model was chosen since it's on par with GPT-4o and it's open source and much smaller. See the link for details about this model. As a rough measurement, you can assume that this process incurs an upfront cost of about 2 milliseconds per character from the docs that are being parsed into a knowledge graph. There is also an option for using a local language model. For this, the smallest language model I could get to work at the time was 14 billion parameters. The model was chosen because it was the best 14 billion parameter model on the Hugging Face leaderboard at the time. If you look at the bottom left, that snippet is the current system prompt for this class. The snippet on the right shows how easy it is to use. In general, there are cases where vector RAG alone does well. There are also cases where graph RAG struggles to shine in comparison, especially when the correct information needed to answer is found in a single document. Graph RAG generally shines when the correct information is spread across multiple documents. However, we should expect that combining vector and graph RAG is always better than either alone. GNNs help the LLM decoder to understand graphs, producing even better accuracy. This diagram covers the fully combined workflow. As you can see, this is the same diagram from before, but I have added in a block to insert the documents retrieved by any sort of document retrieval method. Since our system is fine-tuned, the LLM should learn to reason over both sources of information. In our implementation, we simply inject the retrieved text documents at the end of our prompt, and we have the textified version of our retrieved graph prepending the prompt. We find this to be the optimal system for now, and will continue to refine as we explore further. Here we have some preliminary results from benchmarking against vector RAG. As a reminder, our approach incurs an upfront cost of about 2 milliseconds per character that we parse into a knowledge graph. We will do further analysis soon and share the result in future works. Stay tuned to LinkedIn for those. Here we see that GNN RAG outperforms across the board. The smallest accuracy boost is 1.26x, while the biggest boost is an amazing 2.8x. This was done using a Llama 3.18b model for both solutions. This slide covers a demo made by our PM, Santosh Bhavani. He was able to upload our PyG code to Cursor and have Cursor completely vibe code a graphical interface, showing how easy our framework is to build upon. Now I'll play this short demo.
Welcome to Text-to-KG, NVIDIA's Knowledge Graph Builder. In just a few minutes, I'll show you how we transform documents into queryable knowledge graphs using NVIDIA NIM LLMs. Let's start by uploading our documents. I'm selecting here IBM tech support documents from the TechQA dataset. You can see the documents are now uploaded, and below we can see that we're already connected to a graph database and a vector database that we'll be using later in the demo. Now let's extract knowledge triples using NVIDIA NIM models. A knowledge triple is a structured representation of a fact in subject predicate object forms, such as NVIDIA RTX 5090 is a type of GPU. Here we pre-configured our LLM for triple extraction. We're using a Llama 3.170b model, and then we can configure extraction parameters. Here we have a prompt that instructs the LLM how to extract relationships from the raw text files. We have additional templates available, and you can always configure your own. Let's go ahead and extract the triples. And while that's running, we can similarly extract embeddings for RAG processing later. Once the files are processed, we can manually edit the triples and entities as needed, correcting or enhancing the extracted knowledge graph. Once we're satisfied with the results, we can then export the triples into a file or store it in our graph database. Let's go ahead and store all the documents in our graph database. Our knowledge graph is now visualized. The interactive display below shows entities as nodes and the relationships as edges. Here you can see for the CVE all the different relationships. Finally, you can test your knowledge graph by comparing retrieval approaches. Our tool supports 3 methods: pure RAG with vector search, basic graph retrieval, and our advanced graph RAG that combines semantic and structural information.
So continuing on, the idea of using GNN embeddings as a prefix to transformer sequence models is highly general, and it can be extended to many modalities. The possibilities are truly endless. One example is a model that can answer general questions about scientific data, such as molecules or cell structures. As another example, one could imagine a setting where a business leader could ask an AI general questions about their customers. You could also use this for any set of docs that have links referring to each other, like those in Wikipedia, academic journals, product manuals, or coding docs, to name a few examples. This idea can be extended further to use multiple modalities for a single task. Imagine an Amazon product graph where each node has a text review and a photo, or hyperlinked documents with both text and image. Extending even further, one could use highly heterogeneous graphs such as those in RelBench or Kumo, where node and edge features could be text, images, audio, video, and more. Basically, anything that can be passed through a GNN in PyG could be integrated into this framework. We actually have an interesting spectrum of graph-like data. On the left side of the spectrum, we have the setting of unstructured data in the form of documents that we must parse into a knowledge graph. This setting is inherently less accurate since we rely on an AI model for this parsing. On the other side of the spectrum, we have data like molecules, hyperlinked document graphs, or relational table data like in RelBench. In this setting, we can assume our graph data is highly accurate. In general, each data source will often cover different knowledge. We also know that most enterprises have multiple of these data sources. Using PyG, you could set up a separate GNN for each type of graph data source, all providing context to a master LLM following similar patterns as discussed before. As a final note, today there are 2 kinds of GNNs. The traditional kind are the message passing GNNs. Then there are graph transformers, which are newer. See the QR code for a webinar on the topic I gave with Stanford and Kumo recently. I'm working with the community to get more graph transformers added to PyG. My goal would be to see how these affect the accuracy of the previously discussed GNN plus LLM systems. In conclusion, this work is built and optimized for the NVIDIA PyG container. Also look out for future productization coming soon. As a final note, I want to acknowledge my fellow NVIDIAns who have contributed to this effort and all of the PyG contributors. The PyG community is ever growing, and contributions are greatly welcome. I'll hand it over to my colleague Ben now.
Thanks so much, Rishi. That was great. I'm going to just share my screen here real quick. Could I just get 1 thumbs up that you can see my screen? Rishi, thank you very much. All right. Hello again, everyone. My name is Ben Berger. I'm a data scientist from Kumo. Rishi mentioned Kumo a number of times in his presentation, and I'll sort of give you a brief overview on what the company does and what the technology is. But I'm going to present to you today more of an applied kind of version of some of the topics that Rishi spoke about, and how you can use a system similar to that with a little less overhead, less data labeling, stuff like that. So the main point or topic of my part of the presentation here is exploring the idea of trying to move past traditional sort of explorative or retrospective questions or topics that we typically use in RAG systems. So we sort of use RAG generally as this quasi-BI engine because we know that LLMs they struggle with predictive tasks, particularly on your private data by themselves. And model predictions questions are typically siloed away from a lot of your external stakeholders. So you're sort of left with only being able to tackle these descriptive or retrospective questions. So SQL queries sort of in plain English. And so can we move past that? And with the addition of predictive output and some of the byproducts of predictive output, can we add that as context in a RAG system to move beyond these descriptive questions and potentially ask future or predictive questions, or do things like model explainability and stuff like that, expand the world that our LLMs can interpret these RAG-based questions essentially. And so the idea today is I'm going to kind of show you how Kumo can be a part of a RAG system like that. And so Kumo is a platform where you can very quickly build supervised machine learning models. And I'll show you how these predictions and some of the other byproducts of Kumo can be used in a RAG system to sort of move into this new world of questions or use cases that you can use in a RAG system. So real quick, before I dive into the structure of the RAG system itself, I want to talk about Kumo and then relational deep learning, which is the technology that sort of underpins Kumo a little bit. So Rishi mentioned a couple times RelBench, which is sort of this relational deep learning benchmark. So relational deep learning essentially is the process of taking your relational data, so a schema of tables that have the primary key and foreign key relationships with each other, and transforming your relational data into a relational entity graph. And every row in each of the tables would be a node, and an edge between any of those nodes would be determined by whether there is a primary key and foreign key relationship between them. And then with this construct of a relational entity graph, we apply graph transformers on top of it to solve a very wide universe of supervised machine learning tasks. Given sort of the nature of graph neural networks and graph transformers in particular, this sort of bypasses the need for any feature engineering, because we're pretty much learning on a raw version of the data, and we can streamline the model building process significantly. And I guess for more Kumo specifically, the way that we sort of wrapped around the idea of relational deep learning is we've boiled it down into just a few pretty simple steps. So in Kumo, in the platform, all you have to do is register your relational data, and then you pretty much prompt it. So because there's no feature engineering, because a lot of the typical model development process that we all go through is sort of bypassed here, you just need to define the predictive task that you're trying to solve. So in Kumo, that's abstracted into this SQL-like language, where you pretty much just define the target and you define the entity that you want to predict on, and that's all you have to do to move forward and train a model. And again, we can capture, or we can define or articulate or query, if you will, a large universe of supervised machine learning tasks, so regression and forecasting and classification of nodes, of edges, of all sorts of things. And then finally, you of course have the ability to fine tune and get to the granularity that you're used to with the models. But also once you have the models built, of course you'll receive the predictions themselves from the model. But the other outputs from a system like Kumo and relational deep learning would be the embeddings, so the graph embeddings from each entity from each model, the subgraphs that were used in the graph transformer to actually propagate information and create a prediction. So essentially today and what's next is we'll look at, using Kumo, you can very quickly articulate these sort of future questions that your LLM can't. And there is a byproduct of Kumo that's not only the predictions, but we also have these subgraphs that we can sort of textualize and add as context in the same way that Rishi briefly spoke about. So moving into more of the structure of a RAG system like this. So imagine we have, and I'm sort of restating how I just described Kumo, but imagine you have Kumo, and then you've connected to your relational database. And in this sort of e-commerce toy example, maybe you've asked, a few predictive questions. So you have a customer churn. How likely is it for each customer to churn in the next X days, right? Product recommendations. What is the next item that a user is most likely to buy? Maybe you have some forecasting. So we have Kumo has articulated and answered these forward-looking questions in the form of models and predictions. So Kumo would ingest the data, create these relational entity graphs, train the transformers, and now we have a variety of predictive answers. And then we could write back a lot of this predictive output to a vector database in the same way that we would in a traditional RAG system. So say we have down here the output, the actual raw output of a churn model, right? You have the entity and then maybe the prediction or the propensity to churn, transform that into some English language version of the prediction, and then index that. So a very similar way to most RAG systems you're probably familiar with. And then in addition, we've been talking about these subgraphs because we know that we have this byproduct of the Kumo platform and of relational deep learning that are the actual subgraphs that were used to train the models for each sample and for each entity. You can extract those from the platform, textualize them in the same way that we saw Rishi do, and you can index those as well. So now we sort of have we have both the predictions from all of these models that we've created. So those are the answers to the forward-looking questions. And then we also have the subgraphs for each of those entities, for each of those tasks that sort of provide or could provide the LLM, the reasoning or the context that was used to come to those predictions. So now that we have all of this data stored and ready to go and ready to be queried, we would probably enter into a very familiar and similar RAG process that you might be familiar with. So you would pass a natural language query to the system. Then you might have a flow or a process of LLM agents to do a variety of things to classify the questions to eventually arrive at the appropriate way to retrieve context and to add it to a prompt. So maybe in this instance, because we're kind of asking these explainability or predictive type questions, we would have a classifier asking whether or not the question relates to a single entity or a group of entities, or is it about more of a broader business question, right? And then maybe after that, is there already an explicit answer available to this? So are we explaining an existing prediction, or are we kind of trying to interpolate a out of sample prediction using the predictions that we have? So a series of question classifications like this would arrive you at the strategy to retrieve what data to retrieve. Could be a vector search on your vector database, could be text to SQL, things like that. And then finally, you would actually go and retrieve the context either from your relational data or from your vector database, construct a prompt with it, and then of course finally pass it through an LLM agent to get your final answer. So I've been sort of circling around what the actual use cases of this are. So excuse the crammedness on the slide, but here are a few examples of sort of what we've been playing with and what use cases you could tackle. So let's call this the model explainability use case. So in the same toy example, say that we have fed to our vector database, and Kumo has this a churn model and a product recommendation model and so on. So if someone asks the system, will customer 123 churn? Well, we know that this is about a single entity, which is customer 123. And is there an existing model that answers this question? And that would be yes, right? So because we do have churn likelihood here. So the process would be then, okay, how do we get an LLM and use its reasoning powers to go beyond just saying, here the prediction that we have, can we add any context or explainability to that? So maybe we would go and query the subgraph for that customer. We would certainly get the churn prediction, and then maybe we would sample a few other similar entities and their subgraphs and their predictions to give the LLM a way to reason through a few examples of how the predictions came to be. And then finally, we would get an output that is not only the answer to the question, which is, customer 123 has a blank % chance of churning, but this is also how a model probably came to this answer. And so for your non-technical stakeholders that are trying to interact with your data, but particularly when they're trying to interact with your predictive data, which tends to be a little bit more siloed and black boxed, this is a way that they can interact with that in a English language form and get familiar and comfortable with the tools that they have at their disposal and all the work that you've done to get this predictive output. So similarly, how about this adjacent predictive task use case? So again, say we have this churn model, we have a product recommendations model, and then someone asks us, well, will customer 123 buy a shirt next week? Well, we don't really have a model that is predicting that necessarily. We have the likely next product or the likely products that we would recommend to a user, and then we have churn likelihood, right? So this sort of sits in the middle of those two predictive tasks. But similarly, we can try to give an LLM a context to arrive at an answer like that, of course, without explicitly training a model like this. So it would go through the same agentic flow to classify the question. And then maybe in this instance, we are pulling just all of the predictions that exist for customer 1, 2, 3, and then asking the LLM to make a reasonable assumption about this. So if we're trying to deduce whether customer 1, 2, 3 will buy a shirt next week and the churn prediction is incredibly high, I would expect that our LLM is able to say, well, they're probably not likely to buy a shirt next week. Or if they only buy footwear, maybe that will factor into the response that the LLM gives. So again, this is sort of a way to expand beyond the defined predictive tasks that you may have gone through, and in this case, that Kumo has provided, but also giving both yourselves and other stakeholders a way to, sit on the edges of that and also tackle those adjacent tasks. And then similarly, and potentially most interesting would be, forget sort of the actual entities or the group of entities that you might be curious about, but with all this information, what if your marketing person said, I have some budget to play around with, and I want to provide some customers coupons. Who should get them, right? A classic question that all of our stakeholders might be asking. So similarly, you could pass this through this same flow, and in very plain terms and things that your stakeholders could understand, the LLM might grab a handful of entities that have all of these predictions, and then pass it as an answer and pretty much say, this is what you have at your disposal. This is the predictive output or the models that we currently have. This is how they segment your customer base, and this is how they could be used for like a marketing campaign or who to provide coupons to, right? We want to leverage the fact that these LLMs are globally trained. They have that type of information, certainly, and are useful in generating ideas and speaking to your data that way and combining those two knowledge bases. So these are sort of the use cases that I played around with in exploring this topic a little bit. So I did kind of load up very, very quickly. I tried this out. I took a data set. It's the Event Recommendation Challenge data set from Kaggle. You might be familiar with it. And I put it into Kumo. I trained a couple models with it, and then I dumped the predictions and the subgraphs into Snowflake, into a Cortex vector database, and added a little UI to it to see if any of this works. So I'm going to jump over there, and you can ask this thing a couple questions. Let's reboot it here. That right. Excellent. Okay. So I just added a pretty basic little UI here, but essentially I trained two models on and the schema is essentially you can think of it almost like social media. There are users, there are events, so users attend events, and then users can also be friends with other users. So very classic graphy kind of problem. And so I trained a model that essentially predicted the likelihood of a user attending an event in the next 7 days. And then for each event, the most likely attendees. So similar to kind of the use cases that I was using, if we ask a question like, will this user attend an event in the next 7 days? And again, we have this model. This would be a case where we want to explain the predictions that we already have. So let's fire that off, and let's see what it says. So according to our model, this user has a 60% chance of attending an event. This prediction is based on the user's recent activity, which shows a consistent pattern of event attendance. Additionally, the user's friends have also been actively attending events, which could influence the user's decision to attend upcoming events. So it is kind of providing a very succinct context and explanation for this prediction. I think that it's passing the subgraph and allowing it to interact with the historical data is certainly how the model came to this prediction. And I think this is a reasonable explanation. And then maybe we could try something like more of the business question. How about which segment of my users should I target with event vouchers? So let's try that. So more of the business kind of problem here. All right. So essentially what this is saying is it's suggesting to target users who fall into high influence and low propensity. So this would be users who have attended many events in the past and have a large number of followers, but our models predict that they are currently unlikely to have attended an event in the near term. And I would argue that that's a decent response to this, right? I think it's getting the exact data structure a little bit wrong, but it is sort of, again, adding that more global context that LLMs have into the predictions and the data that are actually at your disposal. So yeah, just wanted to throw something together to kind of illustrate this a little bit more. This is all I have for you guys. So Kenny, I guess I'll hand it back to you.
Thank you, Ben, and thank you, Rishi, for sharing your knowledge and practical examples. Now we will begin answering questions live. So I would like to remind everyone to use the Q&A section to submit your question instead of the chat. This ensures that our speaker can easily see and respond to them. So now I invite Ben to start with our Q&A session by answering 2 questions, followed by Rishi. Ben, if you are ready, you can start. Please do not forget to read the questions before you provide an answer.
Yeah, actually, Rishi, you want to go ahead? I'm still kind of looking through some of them.
Yeah, during your speech, I was looking through. I answered a bunch of them offline, but I chose a few that I think are cool. So Derek Okahuma asks, is the use of GNNs with LLMs more similar to how humans come up with our own predictive models, similar to the +2 sequence example of how we're able to much more easily understand this versus a regular LLM? So this is a complicated question, since I do think GNNs put us closer to thinking in how humans think. You can imagine that the LLM is saying, given this context, what's next? But the GNN is encoding a context of this related to everything, this related to everything, this related to everything. If you think about our brains, they're inherently like neuronal graphs that at a low level are saying, okay, this input from my eyes is connected to this, and it's trained over many years. So we are getting closer, but I definitely think that, this is not the end of, model innovation. Jan LeCun and many others in that space are in of the camp of like world models and kind of condensing understanding in a parametric way. I think humans do a lot of this. A lot of what we do is really just analogizing things to things we know until we know them better. So I think, yeah, there's a lot more left in the research space, but I think this is an important step in that direction. Another question, it was broken up into 2, but I'm just going to answer them together. So can you provide more details on how to project graph embedding via GNN to the LLM embedding space? Does that mean you somehow convert it back to text and add it with the previous prompt? Or is there a way to integrate the embedding directly without converting back to text to the LLM's inference? So we're actually not we're not embedding it in text. I'll share screen back to my slide deck to make this a little bit easier to understand. Okay, sorry. So if you look here, once we embed once we embed it, we have the GNN output. This is going to basically give you features for every node. We then just do a mean reduction to get a single vector. And this vector is just concatenated with the LLM's own encoding space. So prior to this concatenation, the LLM does tokenization, and usually most LLMs have an encoder that takes that token, puts it into a latent space, and then usually there's an LLM decoder. So we're basically just injecting into the middle of the process. And then either you fine tune the LLM so that it understands this, or you freeze the LLM and the GNN to speak the language, the internal language of the LLM, producing almost, so tokens will, you'll take let's say the word you'll convert it into token space, then you'll embed it. Now you just have a vector that the LLM uses to represent that. The GNN could essentially be embedding the whole subgraph into that space in a learned fashion. that would be how I would answer that. So let me just check those off. Ben, if you want to go.
Sure. So there's a question here that essentially is asking whether or not you can try out Kumo locally. The answer is no, you cannot try it out locally, but we do offer free trials on Snowflake. So if you have Snowflake as your data warehouse, you can request a free trial over the Snowflake marketplace. And then there is another Kumo specific question right under that. Who specifies the tasks in Kumo? Who administers the training preferences? What happens when there aren't enough tables to learn from? So you, the user, would be specifying the task. So you still have to define what the target is, what the entities that you're predicting on. Kumo will not decide what the predictive task that you want to tackle is. You have to define that. It's just sort of simplified into this querying type of language where you have to write, 3 lines pretty much of SQL to determine which model you want to train. And then similarly, who administers the training preference, again, before you need to train the model, you have the ability to dive into the hyperparameter search space, the subgraph sampling space, everything like that you would typically do to train a graph neural network. None of that is abstracted from you, and you have the ability to tune all of those parameters as well. And then finally, there was one more sub question to that, though it kind of popped away from me. I think it was.
What happens where there aren't enough tables to learn from?
Yes, thank you. So in that instance, if you had just a single table, there wouldn't be any graph around it. So you'd essentially just be training a few layer neural network on one table. So it would still learn, you could still train the model, but you would not be taking advantage of the graph relationships that do exist in your relational data. So you have the ability to train a model on a single table. Of course, you want to add as much context to that as you possibly can. Rishi, you want to go ahead if you have a couple?
Yeah, sure. So I guess there's interesting question. How does the knowledge graph help in reasoning? So in the way that we're using it right now, it's helping to encode multi-hop reasoning within your context data. So we retrieve some relevant data, and then the GNN embeds this into the LLM space in such a way that this leads to that, this leads to that, and that is a form of like multi-hop reasoning. Now, in today's LLM space, reasoning is generally referring to reinforcement learning and chain of thought. This is something that we're actually working on. I just didn't have time to include it in this talk, but I have slides and stuff on this topic. But in general, with these reinforcement learning approaches, you can imagine that you're actually training the LLM to think in a graph. Let's say, this hypothesis leads to this. Now I'm going to come up with 2 potential solutions. So now you're going to split. And then you're like, wait, let me check that. And then, so you're creating this complex graph on the fly to answer questions. And so, that's naturally a graph. Graph modeling makes, learning on graphs better. So we are working on, future solutions to add GNNs or graph transformers into this reinforcement learning pipeline. It's very cutting edge research. So stay tuned, and I'll make a big announcement whenever we have something exciting. I guess another one is I want to ask, is the choice of positional encoding technique and the normalization layers of the graph transformer GNN, how could that impact in performance? And it's going to have very big impact, right? So with any AI model, just hyperparameter choice, ReLU versus JLU versus there's a million flavors of those. These things do make a big difference. Generally, like, if your data task is easy, you shouldn't need to tune your hyperparameters too much, and you'll find that any set will kind of do the trick. But generally, like when you're working on harder tasks, once you see your accuracy is not going up much, hyperparameter tuning is essential. Really, it's something you really can't get away from in the world of deep learning. Ben.
Yeah, I see what I believe that this was for me, although it could be for you as well, Rishi, but how to assess the relevance of the retrieved subgraph. Is there a metric for this? That's a very good question. And I think that, the $1 million question with most RAG systems is a reliable way to evaluate the output, particularly in the use cases that I kind of went over, like model explainability. I think that it's pretty difficult to evaluate that. So again, not necessarily the subgraph itself, but the entire output. In the way that I had set this up, I actually retrieved the subgraph uh, in like a SQL-like manner, hard-coded the retrieval of the subgraph based on the entity. So I didn't do any similarity search on the subgraph itself in most instances. And yeah, so I kind of tried to bypass that problem because most instances where you need it, you would be referring to a particular entity. But yeah, I think that the question of evaluation for all of this is certainly very good, and it's difficult and very subjective on the techniques that you use. There are many to try to evaluate the performance of a system like this. Rishi, if you have one, hold on, I'm looking.
I could actually just add a little more. Like, so in our work, retrieval, for documents, for example, generally, if you're doing these benchmarks, someone hand pre-labeled, like, yes, this document is good, right? But when it comes to triplets that you extract from it, it's hard to say, like, even if all the triplets came from that original golden document, you can't necessarily say all of these triples are relevant. And so this is pretty much an unsolved problem in terms of like validating the quality of your knowledge graph, as well as validating the subgraphs that you retrieve for each question. You could use some sort of LLM as a judge. For that, you would want to use a very powerful LLM, like, whatever, OpenAI or the NIMs that we use. But even then, generally, LLMs, from what we've seen, LLMs are better at converting raw text into triplets, since it's like they're designed to take in raw text. They're not as good at understanding the triplets that you pass to it. That's just what we've seen. So for our work, because of this, we have to just evaluate the end-to-end solution using an LLM as a judge for the question answering accuracy, which is relatively okay today if you are using like a powerful state-of-the-art model. Yeah.
I can take another one here. One of the problems that I'm dealing with is whether the relational data that we've accumulated is sufficient to solve for the prediction we want to make. Are there approaches here that can either point out missing data or fill in proxies from other sources? Yeah, it's a great question, and of course a very common thing I think that we all deal with. I would say that I wouldn't say necessarily that the RAG system that I talked about is probably appropriate for answering that question, but certainly when you have a platform like Kumo that allows you to specify these tasks and train models very quickly, you do not have to wait 3 months for the model development lifecycle to understand that you cannot solve this machine learning task. You could figure it out in 3 hours. So I would say Kumo as a platform is much more well suited to arrive at those answers to determine whether or not there is any juice to squeeze from your data, as opposed to sort of like a RAG system like this.
I could go through and just
I have one too, Rishi.
okay.
Someone asked, do you think the framework can help to answer aggregation required question, like summary question or counting question? So I did play with this a lot. The problem is that, as I'm sure a lot of you are familiar with, that LLMs are horrible at doing math from numbers that have been passed to them. It is very plausible to say, to ask a question and say, are people with blue eyes more likely to 7 days than those with brown eyes, right? And if you have the attributes in your data, you could certainly encode that information in your vector database, like retrieve relevant information, and then you would just at that point are relying on the LLM to aggregate that information the right way. And I've seen it do it very, very poorly. So I was still working out a way to try to avoid that and actually do it programmatically as opposed to asking the LLM. But yes, this is certainly something that I was playing with, and I think another very obvious use case here. Yeah, so I guess the answer here is that you are just relying on the LLM to do what it's not meant to do. Rishi, you want to take one?
Yeah, so interesting question. Would GraphRag help with code generation? What would the triples look like? So you could try to just pass your Python code into this text to KG thing and see what happens. I haven't personally tried it. But there's a long history of graphs in code. There's an open graph. OGB is the open graph benchmark. It's a long-standing GNN benchmark. And there's one of them called OGBG code 2. And they basically found a bunch of GitHub Python code. And they have traces of how functions, connect to each other. So you wouldn't necessarily like, I would say that's probably a better way. I would say look that up and look at their approach. But in general, yeah, doing things that are more domain specific will generally help you out here. Since code is not well described by just thinking, okay, this is language, right? On another hand, like these models are very good at understanding code, so maybe it'll work. Like that could be your baseline or something easy to try at first. But I would definitely recommend looking into the OGBG code 2 data prep and how they created these graphs from Python code. I think that plus the raw text would definitely be better. Yeah.
We have 3 minutes until the end of our workshop. Ben, do you want to answer maybe one more question?
Sure. Actually, this is an interesting one. It might be for either me or Rishi, but definitely topical. Are there any examples of implementing this using PyTorch Frame, or just an aspect of this is in PyTorch Frame? So I can answer this from the Kumo side. The row encodings in the relational entity graph are all created using PyTorch Frame. So PyTorch Frame is a very important part of the Kumo and the relational deep learning process in general. Rishi, I don't know if you have anything to add.
Yeah, I can follow up on that. There's an open GitHub issue that I'm collaborating with the community on that we will eventually connect, have an example of connecting RelBench style data or Kumo, and yeah, PyTorch Frame is the backend for all of these. So that's on the roadmap, but it is a community project, so generally these move a little bit slower than internal efforts.
Great. Thank you, Rishi, and thank you, Ben. We've reached the end of our workshop, and thank you to everyone for joining and for your amazing question, and also for your positive comments that we received in the chat for our presentation. So I hope you gained valuable insights. Tomorrow we will send you an email with the video recording, the notebook, free trial links, and additionally we will sending a follow-up email with answers to any question we didn't have time to address live. We received many great questions, maybe 100. So thank you again. And also, if you have any question, you already have my email. Please reach out to me and I will connect with our team. Thank you once again and have a great day. And thank you, Rishi, and thank you, Ben again, for your presentation.
Thanks so much. Bye-bye.
Thank you all.